A warm welcome to the lecture on the subject of wavelets and multirate digital signal processing. To put the discussion of the current lecture in perspective, let us recapitulate what we did in the previous lecture. In the previous lecture, we had looked at the equivalence between functions and vectors in depth. In fact, in that equivalence, we saw that by bringing in the notions of the inner product between functions and of course, the inner product between sequences, and then noticing that Parseval's theorem is a version of a similar statement on the inner product, we understood that this analogy between functions and vectors leaves us much to gain, because it helps us picturize very well, it helps us visualize very well what we were talking about when we talked about the ladder of subspaces. In general, in functional analysis, this is a very serious analogy. So, it is not just a simile, so to speak, it is a metaphor. We can actually think of functions as generalized vectors and gain a lot from that kind of an analogy, rather that kind of an equivalence or a generalization. And now, we need to bring in another dimension to this discussion, which we had briefly begun in the previous lecture. The dimension of replacing work with functions with work with sequences. Sequences are easier for us to deal with. In fact, sequences can be dealt with using a computer. You could store the samples of a sequence in memory, point after point. You could process them in discrete time, step by step, and produce an output which is again a sequence. And lo and behold, if whatever you are doing with a sequence maps exactly what you wish to do with the original continuous time functions, then this is an added advantage. In fact, this is true for the spaces V 0 contained in V 1, contained in V 2 and V minus 1 contained in V 0 and so on, as we saw briefly in the previous lecture, but which we shall now go into greater depth today. So, let us come back to that discussion. How could we think of a function in V 0 as a sequence, as an equivalent sequence? Well, very simple. Essentially, what we are saying is, look at the coefficients in the expansion of that function with respect to the basis of the space V 0. So, there you are. We have the following standard basis for V 0, given by phi of t minus n over all the integers, and let us sketch a typical phi of t minus n. It is 1 between n and n plus 1 and 0 else, 0 everywhere else. This is how phi of t minus n looks. Now, in fact, this is also an orthonormal basis. I introduced that word, orthonormal basis. What do we mean by that? If I take the dot product of two of them, phi of t minus n and phi of t minus m, for any two integers n and m belong to the set of integers, then this dot product is equal to 0 if n is not equal to m, and 1 if n is equal to n. Very easy to check. It does not require too much of working to prove this, and I leave it as an exercise for you to show. All that you need to do is to calculate the integral in the product. After all, phi of t minus n and phi of t minus m are in fact non-overlapping when n is not equal to m. And if n is equal to m, they overlap completely, and then of course, the integral is just the integral of a rectangle of unit height over unit length. So, it is 1. Whatever it be, let us consider a function in V 0 again to fix our ideas of the connection between functions and sequences. So, let us take this example, again a little bit of repetition from the previous lecture, but let us fix our ideas with it. So, we have this function, let us say x of t given by the following graphical representation. So, let it take the value, let us say half for some variety between minus 1 and 0, minus 3 by 4 in the region from 0 to 1, 3 by 2 in the region 1 to 2, and let us say 4 in the region 2 to 3. So, it is very easy to see that x of t can be written as half phi of t plus 1 plus minus 3 by 4 times phi of t plus 3 by 2 times phi of t minus 1 plus 4 phi of t minus 2 and so on. So, you could continue this beyond 3 and you could continue it before minus 1. And what we said in the previous lecture was that equivalent to this continuous function is the sequence constructed by dot 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 and then half at minus 1, minus 3 by 4 at 0, 3 by 2 at 1, 4 at 2 and so on. So, in other words, there is an equivalence between x t and the sequence. Now, again just to recapitulate the notation for a sequence, we write the 0 point and mark the arrow 0 here to show that this is the sample at n equal to 0. And then of course, you have 3 by 2 at 1, 4 at 2, half at minus 1 and so on. So, when we write a sequence in this notation, what we mean is that this is the sample at 0, n equal to 0, and then the other samples are arranged in the right order. So, for example, this is the sample at n equal to 1, the sample at n equal to 2, the sample at n equal to minus 1 and so on in the correct order around the sample that we have marked. Now, as an alternative, we could have as well written the same sequence in the following way. This is just to introduce notation properly. So, we could also have written so you could mark 1, for example, the sample at point number 1. And then the sample at point number 2 is 4, the sample at 0 is minus 3 by 4, the sample at minus 1 is half and so on. So, it is the same sequence written differently, just for some variety in notation. Sometimes we might prefer to do something like this. Anyway, coming to the point and stressing it once again, there is an equivalence. There is an equivalence between the function and the sequence. This function belongs to V 0 and the sequence now belongs to what is called the set of square integrable sequences. So, let us call this sequence x of n. In that case, the square integrability of x t. In other words, the fact that integral from minus to plus infinity mod x t squared dt is finite means summation from n going minus to plus infinity is also finite with the argument as mod x n squared. This is also finite. And therefore, we use a term for this. We say x t belongs to L 2 R implies x of n belongs to small L 2 z. So, we introduce this notation. This is a new term we have introduced, small L 2 z. So, small L 2, see, just as you have capital L to denote spaces with continuous arguments, you have small l to denote spaces with discrete arguments. And again, we would like to define LPZ in general. So, in general, LPZ, this Z of course refers to set of integers. So, LPZ is the set of sequences, in fact, it is the linear space of sequences. Let the sequences be written as x n such that summation n going from minus to plus infinity mod x n to the power p is finite. So, in particular, if you put p equal to 2, you get small l 2 z. Now, what we have just shown is that there is a correspondence. So, we have just shown a correspondence if x belongs to V 0, which in turn is a subspace of L 2 R. Of course, here we are talking about a continuous time function x of t. Then we have the corresponding x of n belonging to small L 2 z. Of course, we can make a similar inference for other values of p, but that is not of consequence at the moment. So, we shall not go into it. What is important is when we talk about inner products. Now, if you have an orthonormal basis, so here for example, we have an orthonormal basis. You see, so x of, in fact, here x n is a set of coefficients, is the sequence of coefficients of expansion. With respect to an orthonormal basis. Now, you know, the orthonormal is important here. If the basis is not orthonormal, what we are now going to say very soon is not going to be true. So, the orthonormal basis is important here. If x n is the sequence of coefficients of expansion with respect to an orthonormal basis, of course, of x t, I mean, then there is also a mapping between the inner products. That is what is interesting. So, not only is there just an equivalence, there is also a mapping of the other operations. So, if you have two such functions in V 0, so suppose you had x t and y t both belonging to V 0. Both of them belong to V 0, which of course belong in turn to L 2 R. and they correspond to the sequences x square n and y square n, square meaning square bracket. Then the dot product of x t with y t in continuous time. So, inner product of x t and y t is understood on the continuous time axis, which is of course given by summation minus to plus infinity integral x t y bar t dt is a multiple, is some constant times summation n going from minus to plus infinity x n y n bar. This is important. So, there is also a carry onward of the equivalence to the domain of inner products. So, whatever we are doing in the context of the continuous functions can be done, can be equivalently done or can be equivalently derived or brought forward to the context of the sequences which are associated. So, we can go to the extent of forgetting about the underlying continuous functions and deal with the sequences directly. Now, what is the physical or the practical meaning of this? Well, let us go back to the first lecture where we motivated the very idea of a piecewise constant representation, and we started with a two-dimensional situation. We said let us take images, and we said let us divide those images into very small areas which we represent using picture elements or pixels. On each of the pixels we put down one number corresponding to the average intensity of the picture in that pixel area. And we said that is reasonably representative of the image or the picture if those areas are small. Now, of course, we are representing the original image by a piecewise constant function, and equivalently we could now think of the image as being represented by a two-dimensional sequence. So, a sequence indexed with two integer variables, let us say n 1 and n 2, n 1 going from 0 to 511 and n 2 also going from 0 to 511 in case we have a 512 cross 512 picture representation or resolution on the computer screen. Good. So, what we are saying now is easy to understand. Whatever we wanted to do with the picture, we can equivalently do with these two-dimensional sequences. If you have two pictures and you want to mix and match or do whatever you want to do, you could do it equivalently with these two-dimensional sequences. If you want to gain some inferences, you could gain the same inferences by looking at these sequences. Good, but where does this take us? Now, what is going to be useful to us is to see how we can move from one resolution to the next. That is what is of interest. You see, ultimately our movement in all this discussion is to extract incremental information, and incremental information is extracted by going from one subspace of L 2 R to the next in the ladder. So, let it be a function belong to V 1. Consider a function, let us say y t belonging to V 1. Now, V 1 you will recapitulate is the space of functions piecewise constant on intervals of length half. So, let us take one such, let us take a function from minus 1 to let us say 3. So, minus 1 minus half 0 half 1 3 by 2 2 5 by 2 and 3. So, I will just write down, I will not sketch, I will just write down values, the piecewise constant values in each of these intervals. So, in this interval the value can be let us say 4, in this interval the value is 7, in this interval the value is 10, in this interval the value is 16. Let us say in this interval the value is 14, 11, let us say 3 and minus 1 for some variety. These are the piecewise constant values in these respective intervals. So, in fact, we have this sequence here. The corresponding sequence so, I will use the notation with the standard marker of 0. So, at 0 I have 10 and then I have in order 16, 14, 11, 3, minus 1, 7 and 4. This is my corresponding sequence. So, in fact, what we are saying in effect is y t, if I call this sequence y of n, what we are saying in effect is y t is summation n over all the integers y n. Note phi of 2 t minus n, that is important. Notice that phi of 2 t minus n is by definition going to be equal to 1 between 2 t minus n equal to 0, that is t equal to n by 2, and 2 t minus n is equal to 1, which means t is n plus 1 by 2. So, for example, phi 2 t minus 1 is going to be 1 between 1 by 2 and 2 by 2, half and 1, and that agrees with what we just wrote down. Good. Now, suppose we decompose. So, we know that we have this decomposition of V 1 into W 1 and V 0, or rather W 0 and V 0, I am sorry. So, we said that we have this space W 0 given by the span of psi t minus n, n over all the integers, and V 0 of course is the span of phi t minus n for all integer n. And now, we are going to introduce the notion of what is called an orthogonal complement. So, we are going to say, well, V 1 is the orthogonal sum. This represents orthogonal sum, and we are going to explain this in more detail. We say that the space V 1 is the orthogonal sum of the spaces V 0 and W 0 if there is a unique way to take a vector in V 1 and decompose it as a sum of a vector in V 0 and a vector in W 0, with the vectors from V 0 and W 0 being perpendicular, being orthogonal. In other words, their inner products being 0. So, what is this idea of an orthogonal sum? The idea of an orthogonal sum is to decompose a linear space into subspaces, of course, of smaller dimension, where you also have mutual perpendicularity or mutual orthogonality between the space, between the vectors in these two spaces of decomposition. Now, I shall give you a simple example from a 3-dimensional situation. Let us take the 3-dimensional space of the room that we are in at the moment, and let us take the 2-dimensional space of the floor. The 3-dimensional space of the room is the orthogonal sum of the 2-dimensional space of the floor and a 1-dimensional space comprised of all multiples of a vector perpendicular to the floor. So, as expected, a 3-dimensional space is an orthogonal sum of a 2-dimensional space and a 1-dimensional space. The 1-dimensional space is formed by all multiples of a vector perpendicular to the floor. The 2-dimensional space is formed by all vectors lying on the floor. So, if you take any vector lying on the floor and any vector in that 1-dimensional space of multiples of a unit vector perpendicular to the floor, these two vectors are orthogonal, perpendicular. In 3 dimensions, very easy to visualize. Now, you can always generalize to n dimensions. So, for example, if you have a 10-dimensional space, it could be an orthogonal sum of a 4-dimensional space and another 6-dimensional space, where if you take a vector from that 4-dimensional space and a vector from the 6-dimensional space, they are perpendicular to one another. Perpendicular as understood by taking the inner product between these two vectors in that 10-dimensional space. Now, I must at this point make a little remark. The inner product allows us to bring in the notion of an angle between functions, a more general version of orthogonality. So, we say two vectors are perpendicular if their inner product is 0. In general, we can also define the angle between two vectors using the inner product, and we shall do exactly that in a minute.